Saida Ismaili Mohadam is a visiting researcher at the University of Pisa, where he is working for his PhD thesis on super-absorbent biopolymers, and he has published several papers in the fields of nanocomposites, hygienic productions, and cellulose industries. So I leave the floor to Saida Ismaili Mohadam for his presentation concerning the different nanocellulose absorption properties for superabsorbent in hygienic applications. You can start.
Thank you very much, Professor Sajjani, for presenting me, and I want to also thank Professor Patrizia Cinelli and Dr. Serena Danti for providing this incredible opportunity for me. Well, this presentation is is related to different nanocellulose absorption properties for super-absorbent in hygienic applications, supervised by Dr. Mehdi Junoubi and Dr. Serena Danti. In hygienic industries, baby diapers, adult incontinence, and sanitary napkins are the most important products. For producing one baby diapers, more than 15 different materials should be connected together to produce one baby diaper. As you can see in the picture, there is a hydrophobic polyethylene backsheet that the function is to prevent liquid to escaping actually from out of the diaper. There is a hydrophilic polypropylene top sheet that allows liquid to go through it and reach to the absorption core. There are a fastening system and acquisition distribution layer that distribute liquids into 3 directions. And one of the most important components of the baby diaper is absorbent core, actually, which is a mixture of fluff pulp, which is a kind of paper, high grammage paper, and super absorbent polymers. Unfortunately, nowadays, the super absorbent polymers are based on acrylic acid or sodium acrylate, which is not bio-based and biodegradable. And there are a lot of environmental problems with using this kind of super absorbent polymers. And with regarding this fact that each child uses more than 4,000 diapers in their lifetime, the environmental problems that arise in this situation are many. Acrylic-based superabsorbent polymer had some advantage and disadvantages. The absorption capacity is good, is okay, it's 60 gram per gram. Retention capacity is good, around 40 gram per gram, but reasonable production cost. But the problem is that I mentioned before, these kind of superabsorbent are not bio-based and biodegradable. Here is an introduction of different polysaccharides like sodium alginate. Sodium alginate is a natural polymer of D-glucuronic acid and L-monouric acid, which contain, as you can see in the picture, contain 2 hydroxyl groups and 1 carboxyl group. I would like to mention about different kind of nanocellulose. This is bacterial nanocellulose, and it has more crystallinity, long length fiber, and low diameter fiber. Crystal nanocellulose that produced by acidic hydrolysis, and it has a large crystallinity. And finally, cellulose nanofiber that contains both amorphous and crystalline regions, and in the terms of length fiber is located between bacterial nanocellulose and crystal nanocellulose. There are limited number of companies like Spongel company in northern Italy that produces bio-based, fully bio-based superabsorbent polymers. For producing full bio-based superabsorbent polymers, natural polymers like sodium alginate and carboxymethyl cellulose, which contain carboxylic group, are dissolved in water and physically cross-linked with such ions like calcium. The material is calcium chloride. This physical cross-linking produce bubbles, and there are some advantage and disadvantage. Absorption capacity is good, around 70 gram per gram. It is full bio-based, but the problem is that the retention capacity in this kind of superabsorbent polymers is poor. To take advantage of two methods that are mentioned before, we can use Graft co-polymerization. Graft co-polymerization is a promising method for producing a high absorptive capacity of superabsorbent polymers. In this way, natural polymers like sodium alginate and for example, carboxymethyl cellulose can be grafted with monomers like acrylic acid or sodium acrylate, and we can obtain benefits for both of these kind of materials. Advantage and disadvantage: the absorption capacity is very high, more than 120 gram per gram. Retention capacity is also is very good, around 70 gram per gram. The cost is about 60% more than the acrylic-based superabsorbent polymer, but in the next slide I'm going to explain that although that it is 60% more than acrylic-based superabsorbent polymer, is good for companies to use these kind of SAPs. But the only problem is that these kind of SAPs are semi-bio-based or semi-biodegradable. In this research, we used acrylic acid as a monomer, sodium hydroxide, for neutralizing acrylic acid, ammonium persulfate as an initiator, methylene bisacrylamide as a cross-linker agent, sodium alginate as a polymer, different type of nanocellulose, crystal nanocellulose, cellulose nanofiber, and bacterial nanocellulose as a filler, and sodium chloride for producing saline solution for the absorption capacity test. First, acrylic acid partially, around 10% neutralized by sodium hydroxide in ice bath for 30 minutes, and three kinds of solutions like 2.5% ammonium persulfate solution in distilled water, and 2% methylene bisacrylamide solution, and 8% sodium alginate solution was ready. Neutralized acrylic acid was put into a beaker, and after that, sodium alginate and different kind of nanocellulose were added to the beaker, and the solution was kept stirring for 1 hour until an homogeneous mixture was obtained. And after that, cross-linker and initiator were added to the solution, and the temperature of the system rose until 70 Celsius degree for 90 minutes. After that, the produced gel was immersed in ethanol for 24 hours, and again was placed to an oven for 24 hours to dry. And after that, was crushed with a mortar and sieved to a standard particle size. For measurements, formulas number 1 and number 2 are related to free swelling capacity and retention capacity, respectively. MT is the weight of swell jet at the time of T, and MO is the initial dry weight of the polymer. For measuring the absorption speed or absorption kinetic, we use the formulas number 3, number 4, and number 5. And finally, we measured actually gel fraction with formula number 6. For morphological study, we use SEM, and for physicochemical investigation, we used infrared spectroscopy, and data were analyzed by SPSS software. In this slide, you can see the formulation of superabsorbent polymer in this research, and you can see the only variable is the different type of nanocellulose, crystal nanocellulose, cellulose nanofiber, and bacterial nanocellulose. In this picture, you can see the SEM images for these two is related to SAPs containing crystal nanocellulose, and these are related to SAPs containing cellulose nanofiber. As you can see, the pore size in SAPs containing cellulose nanofiber is a bit larger than pores in SAPs containing crystal nanocellulose. And interestingly, the bacterial cellulose is located into the entrance of the pores, and after swelling, these bacterial nanocellulose swelled and blocked the entrance and doesn't allow water to penetrate into the polymer. As you can see, because of a long length fiber of bacterial nanocellulose, low fiber diameter, and good viscoelastic properties of bacterial nanocellulose, there are like a curl and kink phenomenon. It means that there are cross-sectional point or connecting point between bacterial nanocellulose. And in the next slide, I'm going to the result of water absorption capacity, which is matched with these results. For FDIR spectroscopy, we have two groups, carboxyl groups and hydroxyl groups. As you can see, the peak intensity of hydroxyl groups and carboxyl groups is fewer than the peak intensity of these two groups in superabsorbent polymer containing crystal nanocellulose. As I mentioned before, C and F means cellulose nanofiber contains amorphous and crystalline regions together, and these amorphous regions increase the reactivity of the cellulose nanofiber in the superabsorbent polymers. But in SAPs containing crystal nanocellulose, the peak intensity is larger. It means that CNC cannot bond with sodium alginate or acrylic acid. In this graph, you can see the result of absorption capacity. As you can see, the highest absorption capacity is related to SAPs containing crystal nanocellulose, and the fewer one is related to SAP containing bacterial nanocellulose. As I mentioned before, the SAP containing bacterial nanocellulose is a blockage of pore size, and there is an interesting result that in 24 hours absorption capacity, the absorption capacity of SAP containing crystal nanofiber is higher than the absorption capacity of CNF. It means that in 24 hours, the water has a lot of time to penetrate into the polymer. For retention capacity, we have the same scenario. Absorption capacity is distilled water is the same in saline solution. For absorptionetic, before I mention absorptionetic, I would like to mention that the ratio of retention to absorption capacity, this ratio is higher with SAP containing bacterial nanocellulose because of its reactivity. It's more reactivity with sodium alginate or acrylic acid. And the result of gel fraction is not against that result. And in this picture, you can see the absorption capacity during different times. And in the next slide, you can see the logarithm of T, means time, to logarithm of absorption capacity at the time of T, to the MSAT, means saturation point. And the X coefficient in these equations means the N value according to the Fick's law. The N value must be less than 0.5 to be able to measure with accordance with Fick's law. And in this picture, you can see that this graph means that the steeper the slope, the higher what absorption rate in the SAP. And in the next slide, you can see the results of the water diffusion efficiency. You can see that this item is high in SAP containing cellulose nanofiber and bacterial nanocellulose compared to SAP containing crystal nanocellulose. As a result, there is as I mentioned before, there is a ratio of fluff pulp to superabsorbent polymers. That this ratio is 40% to 60%. In industries, we use, for example, in diaper size 5, we use 11 gram superabsorbent polymers and 15.5 gram fluff pulp to pick the ratio of fluff to powder wheat would be 40 to 60. And to reach the 660 gram absorption in the diaper. But in this research, the maximum absorption capacity of the SAP was around 100 gram per gram. So we can decrease the amount of superabsorbent to 6.7 gram. instead of 11 gram, and we can use the 10 gram fluff pulp instead of 15.5 gram to reach the absorption capacity of 660 grams. So in this way, the companies could save daily more than 10,000 American dollars for each production lines. Thank you all for your attention.
So, thank you, Said, for your presentation. Any questions? Yes.
Sorry, my name is Adrich. I'm from Celabor, Belgium. Thank you so much for the presentation and also for the very interesting result. I have just a couple of questions.
Of course.
So, did you investigate the mechanical properties of the gels that was formed after the retention and after the absorption of the water? Because we know that after retention, the baby diaper, when the baby will sit on the couch, we have a pressure, and we need to know the retention if it's the properties of the gel are also sufficient for this kind of pressure.
Exactly, good question. But consider that I'm a visiting researcher here. There is a test which is called absorption under load, which simulates the baby's activities, sitting, standing, walking, running. But unfortunately, I couldn't manage to measure that test here, and maybe in the future I can do that.
Perfect. And the other question, just for the cellulose nanofiber that was used, which kind of cellulose nanofiber it was, and how it was produced?
Different kind of nanocellulose, actually. As I mentioned, we used cellulose nanocrystal, cellulose nanofiber, and bacterial nanocellulose. That best result was related to SAP containing cellulose nanocrystal, because it didn't bond with sodium alginate or hydrogen bonds or esterification bonds with carboxyl groups of the acrylic acid.
Okay, thanks. And just for cellulose nanofiber, the nanofiber, but not the nanocellulose. I know that you have used different kind. The cellulose nanofibers was charged negatively, or?
I bought a cellulose nanofiber. You mean if you?
Okay, we'll discuss after to see you bought from which company to. Yeah. Okay. Thank you so much.
Okay, you're welcome.
Any questions? So, I have a curiosity. Do you think that these bio-based super absorbent materials could be used in other applications, for example, in agriculture, as a slow release water reservice, or as I expect, their cost is too high for this application?
Yes, of course. There are so many applications for these kind of SAPs, but please consider that for SAPs for hygienic applications is more complicated, because we have to have water absorption capacity and retention capacity together. But in agricultural applications, we don't need the retention capacity to be very high. Of course, we can optimize these SAPs to have higher absorption capacity, and fewer retention capacity can be used in agricultural applications. No.